We'll be looking at question 17, June 2022 paper. Now, this is a enthalpy change question. So you've got magnesium reacts with silver nitrate as shown below. You've got this equation, and you've got the enthalpy change in kilojoules per mole. A student adds excess magnesium to this volume and this concentration of silver nitrate. So the limiting reagent is silver nitrate, and the initial temperature is 20 degrees Celsius. Determine the maximum temperature reached in this reaction. Give your answer to 3 significant figures. Assume that the specific heat capacity and the density of the solution are the same for the water, and there's no heat losses to the surrounding. Now you see, this is a question using Q equals mc delta T. Now, usually we're given, we normally have to work out the enthalpy change, but they've given you the enthalpy change. So what we're actually doing is working backwards. So how we do this will be as follows. Let's work out the volume, concentrate. Let's work out the moles from silver nitrate. So for silver nitrate, you've got volume, you've got the concentration. That gives you 0.04 moles. Now, you see, we've got 0.04 moles. This enthalpy change given in the question is for 2 moles of silver nitrate per 2 moles. So we want to work out, so we do the minus, or we're just looking at the energy change. So just use the value 678. That's kilojoules per mole. Let's multiply that by the moles, 0.04. And you see, this is per 2 moles of silver nitrate, but we only want per 1 mole. That's why we divide by 2. This gives your answer in kilojoules, and we then multiply it by 1,000 to convert kilojoules into joules. 678. That gives you 13560 joules. Just a reminder of what you said. This reaction, this minus 678 kilojoules per mole is per 2 moles of silver nitrate. We just want to work out per 1 mole, because that's the limiting reagent in this reaction. Now, once we've done that, we then plug these values in. So you got Q equals mc delta T. So Q is 13560. M is the mass. We assume 1 centimeter cubed is equal to 1 gram, because that's the medium in which the temperature difference is being measured. Got the specific heat capacity of water, 4.18 joules of energy needed to heat 1 gram of water by 1 degree Celsius. And then you've got your delta T value. That's the difference in temperature. By rearranging, we can work out delta T. So 13560 divided by 100 divided by 4.18. That gives you 32. Delta T equals 32.4 degrees Celsius. And the maximum temperature will be this. We need to add on the initial 20 degrees Celsius that we started off with in the question. So that will be plus 20. That will give us 52.4 degrees Celsius. Yep, and the mark scheme supports that. Where are the 4 marks from? one is from volume times concentration, one is working out the energy change. Remember to divide by 2. One is to work out the enthalpy change, and one is to add the 20 degrees Celsius. Moving on. This is an interesting question. The student wants to repeat the experiment, but there's not enough silver nitrate. So the student decides to modify the experiment, again adding excess magnesium, but half the volume, same concentration, but half the volume. So you see, if there's half the volume of the same concentration, you're going to get, let's do Q equals M times C times delta T. How would it affect the maximum temperature? You see, we are halving the mass. If we're halving the mass, the energy change will also be half, because halving the mass will mean that there'll be half the number of moles. There'll be half the number of moles, and so the temperature difference would actually be the same. So, yeah, the temperature difference will be the same, because originally you had 100 centimeters cubed. You've halved that volume, and you're only using 50 centimeters cubed. And so if you're using 50 centimeters cubed, the mass will be half, and the energy given out will be half, but the temperature difference would be the same. I hope that makes sense. See what the mark scheme says. It says so this is from the mark scheme. Max temperature is the same. Max temperature is the same because you've got half the energy or moles, and half the mass of the volume. Yep. Moving on. So this question, even though it's one marker, there's quite a bit to think on. It's all about proportionality, or this change affects this. But when you do actually, you know what? Just to make sure that you understand this, you know, let's do this by calculation. 13560. So if the mass is a half, 50, and you got 13560 by 2, 4.18, and let's recalculate delta T. So you can do this by calculation. 13560 divided by 2 divided by 50 divided by 4.18. Yep, again, delta T is equal to 32.4 degrees Celsius. So you can do this by calculation as well. Okay, moving on. This question here is referring to the enthalpy change of formation. You're using enthalpy change of formation values, and you've got this reaction here, and you're given the enthalpy change of that reaction also. Nitric acid is manufactured from ammonia in a multi-stage process. The equation for the first stage in this process is shown in this reaction. Explain the term enthalpy change of formation. Enthalpy change of formation is where 1 mole of a substance is formed from its elements. Okay. if they said standard enthalpy change of formation, then you could add from its elements in their standard state. It's asking you calculate the standard enthalpy change of formation of NO. Now, what we're doing, usually we have to work out the enthalpy change, but they've given you the answer and they want you to work backwards. So what I'm going to do, I'm going to rewrite this equation and we'll work from that. And we'll make our cycle. So we've got our, actually we've got the value here as well, minus 1172. We've got our elements here. This is made from nitrogen, hydrogen, oxygen. We've got 2 moles of nitrogen. We've got 3 moles of H2, and we've got 5 moles of O2. Just checking the right-hand side is balanced. Yes, it is. 4 plus, yep. And so, when you've got your elements, the arrows go upwards. Why do they go upwards? Because you're using these elements. These are your elements, and they are forming the reactants, and they are forming the products. Hess's law states that the overall enthalpy change of a reaction is going to be the same, irrespective of what route is taken. Can you see we are going against the first arrow, but we're going with the second arrow. So it's going to be minus reactants plus products, or products minus reactants. So ammonia is given as minus 46, but there are 4 of those. Oxygen, the enthalpy change of formation of oxygen is 0, because going from O2 to O2, there's no energy change required in that. So 0 times 5. And then for the products, you've got 4x. This is your nitrogen monoxide, what we're trying to work out, the enthalpy of change of formation, plus 6 times water, which is minus 286. And so we'll write this down, products minus reactants, products minus reactants, minus 46 times 4. We won't include the 5 times 0, which is 0 anyway. Be careful of the signs. You can very easily make a mistake here. This gives you minus 1172. So what we do from here, we just rearrange and calculate 4x. So let's try neatening this up. 6 times minus 286. You got a minus minus. So let's make that plus 46 times 4, 184, plus 184 gives you minus 1172. Minus 184 and plus 1716. Wait a minute. Minus, yeah, plus. Whatever you do to one side, you do to the other. 1716. So 4x is equal to 360. And x is equal to 90. Plus 90 is your enthalpy change of formation of nitrogen monoxide. And that is correct. In the exam, you know, I've shown you I've drawn the cycle. It's not essential, but I showed it anyway for you to emphasize, you know, why it's products minus reactants. This is worth 2 marks. You should be able to do this a lot more quicker than I showed here. But I've shown you the long way just so that you understand. moving on. We've got entropy. This is a question on free energy. Carbon disulfide reacts with dinitrogen oxide. You've got the equation there. You've got the state symbols. It says explain you've got the standard entropies of the individual compounds. It says explain the term entropy. Entropy, this is a definition you want to learn. And by learning the definition, you'll be able to explain what is going on as well. Entropy is the quantitative measure. Quantitative measure of the degree of disorder. How much disorder is there in a system? Does the degree of disorder increase or decrease in a reaction? We have a look at. Calculate the free energy is given in the question. You've got the temperature there as well. Calculate the enthalpy change, and calculate the enthalpy change, and we would need to work out the entropy change also for this. This is worth 3 marks. Now, the delta S, first of all, will be equal to products minus reactants. Just checking they haven't given that answer. No, they haven't. And remember, this is in joules per Kelvin per mole. So this is products minus reactants. 6 plus 4 CO2 plus 8 times 192 and minus, that's your products, minus 4 times 151, let's put double brackets, plus 8 lots of N2O, which is 220. Gives you 220, but this is joules. Joules per Kelvin per mole. So we'll need to do some changes to that. Now, yep, that's correct. So, oh, wait a minute, this is wrong. The answer, I'm off slightly here. Let's just double check. What have I done wrong here? Sulfur is 256. Then we've got 4 CO2. Yep. And then we've got 8 N2. Yep. Minus 4 times 151. That's correct. And then N2. Oh, yeah. So I think I've just done a calculator error. Oh, no. My calculator says 284. I wrote down 220 looking at this. I had a small lapse of concentration there, ladies and gentlemen. Apologies. 284. My calculator had that answer on there. Now, we've got delta G is equal to delta H minus T delta S. As you know, you need to know this expression, linking free energy to enthalpy change, temperature, and entropy. They give you the delta G value, which is minus 2672. Enthalpy change we're trying to work out, and temperature they've given as 25, but we need to multiply that. We need to convert that into Kelvin, so that would be 25 plus 273. That's your T value, and multiplied that by delta S, which we've got 284, but we need to convert the joules into kilojoules. We divide that by 1,000. So that becomes 298 here. Let's work this out. Minus 2672 plus the 298 times 0.284. Delta H is equal to, they want the answer to how many, we can give it to the nearest whole number. So we'll give that as minus 2587. Yep. Now entropy, and just let's have a look at why it's a positive value, because you've got 8 moles of gas, 4 moles of a liquid, but that's going on to form 1 mole of a solid, but 4 plus 8 moles, which is 12 moles of a gas. So liquids and solids, there's not that much change in entropy, the degree of disorder. But when you're going from 8 moles of a gas to 12 moles of gas, it's gaining significant amount of disorder. So that's why that gaining is why the entropy is positive. Why am I saying this? The student concludes that the reaction 17.2 is feasible at all temperatures. Let's have a look at, explain whether the student is correct or not. Now you see in the expression delta G is equal to delta H minus T delta S. Now, because delta S is a positive value and delta H is a negative value. Now, when you're subtracting a positive value, temperature is what we're trying to, doesn't matter what the temperature. So this is like our variable, whether it's low, whether it's high, delta G will always be negative. And putting that into words, you will get you'll get your 2 marks. Have a look at the mark scheme. Let's see what the mark scheme, how it words this. You get a mark for saying, obviously put this into words, not just, so what does the mark scheme say? Delta S is positive and delta H is negative. You get 1 mark for that. And second mark is delta G is always negative at all temperatures. Putting that into words, you'll get your 2 marks. Yep, that is the end of question 17. I'll see you next time.